So welcome back. So we are now reached the stage, the most important stage, understanding Q-learning algorithm. Okay. So we have seen the design of Q-learning algorithm or any RL algorithm which involves choice of state, state space, action, action space, transition function, reward function, and you know the terms policy, optimal policy, and you know optimal Q value. Optimal Q value is denoted as Q star XA or QXA, and we know that if we can learn QXA, then we know the optimal policy. Optimal policy will be argmin of QXA. So let us see the algorithm. So we don't know the Q values. Initialize QXA to random values for all XA pair. In our example, we have 35 states and 4 actions. So you can store Q values in a matrix, in a table of 35 rows and 4 values. Do it so that you can see the Q values. Okay. Initialize epsilon to 0.5. This we have seen epsilon greedy algorithm. Okay. So initially epsilon is 0.5. Set alpha learning index to 0.1. As far as this small example is concerned, we will reach the goal in 15 steps. So the current reward is as important as future reward. So I take discount factor to be 1. So here we will repeat this inner loop. We will repeat this inner loop maximum episode time. This is a parameter which you should choose. Say maximum episode for this example, some 1000 episodes will be sufficient. Then we are starting every time, we are starting from cell number 1. And the step count k is equal to 1. I is there, which is the episode count. K is how many the steps we are keeping track of it. Select an action using epsilon greedy algorithm. So here, when you're implementing, you should know what is epsilon greedy algorithm. With probability epsilon, you will take greedy action. You will take random action, and with probability 1 minus epsilon, you will take greedy action. So with probability epsilon, you will take greedy action. I will repeat again. With probability epsilon, you will take a random action, and with probability 1 minus epsilon, you will take greedy actions. How will you do this? To do this, you have to generate a random number between 0 and 1. Your epsilon now is 0.5. If the generated random number is less than 0.5, you will take a random action. And if it is greater than 0.5, you will take the greedy action. You have some Q values. Initially, this Q values doesn't make any sense because it's all initialized random. So that is why initially epsilon is taken a large value 0.5. So when you take an action, you will reach, suppose you are in 1, you take an action, say down, you will reach 7. When you reach 7, the environment, the code should give you the G value, the reinforcement value. G, when I am from 1, I go to 7, the G value will be G, 1, down, 7, which is 1. Update Q using equation 2. Equation 2 is Q nu XA is equal to QXA plus alpha into G of XK, AK, XK plus 1 min A prime Q X nu. You know that equation. If you want, I will show that equation again. This is my equation 2. We update the Q value using this equation. Then X is equal to X nu, K is equal to K plus 1. Are you in goal? You reach 7. Then use epsilon greedy algorithm. So the random number will generate. You will generate a random number between 0 and 1. Say it is the random number generator is 0.7. That means you will take the greedy action. So based on the greedy action, suppose the greedy action says take right, you will go right. You will obtain the reward for this. I will use pen. First I took this action, I reached here, then I took an action right, I reached here. When I took this action right, I got a reward. which is again 1. Then it's not a goal state, so I'll come back again here. Then again I took a down action. Then what happened? Then I took a left action. Every time I'll get a reward and I'll keep on updating the Q value. I took this action. I took this action, up action. Then algorithm said take this action. Algorithm said take this action, take this action. So initially it may move around, round and round and round. It took this action. It took this action based on epsilon greedy algorithm. You are in 27, let me repeat again. According to the epsilon greedy algorithm, the action to be taken is right. So it took this right action. Obtain G, update Q value. Then you copy X new to X. Then again, based on epsilon greedy, it's right action. Then again say it was a right action. Then again it was right action. So it's a wall, so it won't go anywhere, it will remain there. Then it took an up action, down action. We reached here. So this, the first trial took some, say 20-25 steps. In simulations, I'll show you the results. Initially, it may take some 100-112 steps to reach the goal state. This is called one episode. So once I finish one episode, I'll update the epsilon. Epsilon was 0.5. After I finish one episode, I'll reduce the epsilon. I'll reduce the epsilon from 0.5 to, I'll reduce the epsilon from, initially it was 0.5. From 0.5, I'll reduce to 0.5 into 0.9, say, which is 0.45. Then I'll do this again. So after some time, every episode I'll reduce epsilon. So after many trials, the epsilon will come down. This is my epsilon graph. So it becomes say 0.1. So then I am, what to say, according to epsilon greedy, with probability epsilon, I'll take random action. Now what is the value of epsilon? It's 0.1. When epsilon is 0.1, I'll take random action with probability 0.1 only. So most of the time I'll take greedy action. So suppose it will be good action. So if you repeat this large number of times, the algorithm will learn Q values. So you think how that happens. Let me show you the results. So this is x-axis is episode, y-axis is number of steps. So initially it took 150 steps. Then some episodes it was less, and slowly after 200 episodes it took say roughly 8 to 9 steps. After 700 it took 8 steps. The total cost was initially small values, so then when it's reached 0.8 it remained there. This is how I reduced epsilon. This is called the cooling schedule. Instead of, when I explained, I said from 0.5 I made 0.45. I didn't do like that. I had epsilon 0.5. For 50 episodes, I maintained it at 0.5 itself. After the 50th episode, I reduced it to 0.45. After 100 episodes, I reduced it to 0.45 into 0.9, so on. So this ripple, so one issue in Q learning is how to reduce this, how to reduce epsilon. Suppose I have reduced epsilon quickly, I could have avoided these ripples. But one point is, if you reduce epsilon too quickly, you may land up in local minimas. That is not the best path, but okay path. So you think about it. I'll put some questions. You have to answer it in the comment box. So this is another more interesting example which I will explain later. Let me ask you some questions, okay? Try to answer these questions. Before questions, yes. The first question is, how should I decrease? How should one decrease epsilon? I'll ask you a simple question. I'm not reducing epsilon, I'm keeping a constant 1. How will the algorithm proceed? Same. If it's held constant at 0, what will happen? So you play around, you write this code and play around with reduction of, because this is a very simple problem. Play around with a reduction of epsilon and see. So thank you. If somebody outside my course is watching this video, it won't make sense for you to watch the remaining part of this video. So let me talk to my students of TKM College of Engineering, MTech Artificial Intelligence. Why I made this video is, I have taught you this in class. What I want you is, you have to consider your reading paper for your review. So what you should consider is, if you are applying, some students said, sir, can I use RL for health? You could use anything, okay. So your paper, when you are reading papers, you may see whatever paper you are reading, you should identify in your problem what is state space, action space, reinforcement function, transition function. You should identify it. Whenever you are giving a presentation, you should tell clearly for your problem what are these design quantities: state space, action space, a reinforcement function, and transition function. Then your paper may be using algorithm like DQ network. So you are smart now, you are MTech students, you should be able to read and understand. There are excellent references, say a paper by, you can search Google. If you search Google DQN, or if you ask ChatGPT about DQN, MIN's paper is there. You could read that, or you could watch any tutorial. There is some of you may be using DDPG algorithm, Deep Deterministic Policy Gradient. So you can't wait till I teach you this, okay? So you have to study on your own. Maybe some students may be using actor critical algorithm. Some of you may be referring papers which is using proximal policy optimization. So the various algorithms are there. It's a growing field. So if you know the basics clearly, you should be in a position to learn all these things. So in your presentation, we'll start the presentation from next week. So you should be good in all these things. You should read and understand these concepts, okay? That is one reason for making this video. So I wish you all the best. Good luck. Thank you.